Okay, welcome to Stability Structures. We are starting a new class, and this class is a practical class where we try to show what probably we are using on site, but most of us probably don't know why we are using it. In this A-series class, we are going to be talking about why we use so many things on site. We are going to do a lot of video about structural members in this A series class. In our B series class, we are going to talk about the analysis, and C series class probably the design. But here we just want to explain some of the things that we see on site, or probably sometimes when we read or study, we really don't get it. So we are going to be using pictures, videos, and anything that can reach our hands, and also to the best of our knowledge, to explain some of these things. Today's class, A Series 1, we are going to be talking about why we use reinforcements in footing. And I will be explaining using this model from Proto structure, which I have modeled. This is slab. What you have here, let me select it, is your slab, and this is your beam. We have them round, and this is our columns. These ones are our columns. Then these ones are our footings. Now, the way structural members or our buildings transfer their loads is from up to down. The slab will distribute. This is a cantilever. I'm trying to model something there. Okay, the slab will transfer its load to this beam, to share it to all of these beams at within the perimeter here, and these beams will take their load and give to the columns, and the columns will pick the load from the beams and transfer it to the foundation, which is what we have here, and the foundation will pick the load and distribute it to the ground. Now, when all these activities are going on, there are things that happens. We are going to discuss that of slab, beams, but we want to start from foundation up. So we are talking about path footing today, and today's class is A series 1. So these footings, as these loads are coming upon them, it was observed that they behave in a certain way because of the way this load. There are things, these footings can undergo what we call bending. They can undergo what we call one-way shear, and then they can undergo what we call punching shear, which is also called two-way shears. Two-way shear, sorry. Now, let us go back to our sketch, because we are going to be doing a lot of sketch, also show pictures on how these things works. So let's go here. Now, in this is our footing, right? And this is our column. This is the load that is being transferred from the slab and the beam and all of that, and they are acting axially. We are assuming that they are acting axially on this column. Now, there are several ways which this footing can act this column can be sitting on this footing. It can sit axially, it can drift away, that is with some eccentricity on this, but whatever way, in our B series class, when we'll be talking about design, we are going to state different um, footing positions and how we can analyze them. We're also going to talk about combined footing and why you always have top reinforcement and bottom reinforcement in combined footing. But for the now, we want to take it from this simple stage to a complex stage. So if we assume that a load N is acting on this footing, is acting on this footing, as this load is acting on this footing, the soil itself is producing an upward force that will counter this particular force so that they will be in a state of equilibrium and keep our building stable. Otherwise, if this load exceeds that of our soil pressure coming on it, there will be collapse. So as this force N is acting, there will be an opposite but equal force that will be acting under this footing. Now let me try to make a sketch of it so that we can see what I'm talking about. Now these forces will be acting under the base. These forces are from the soil acting under the base, trying to push and keep this base in equilibrium as a result of all this load from columns, slabs and all of that acting on the footing. Now when this happens, there is tendency that there are three things that can happen to this footing. One is that there is tendency that this footing can bend. Two, there is tendency that this footing can shear. Three, there is tendency that this footing can punch. Now that's why we want to talk about this behavior of this footing under the action of this load. So we are going to be looking at the behavior of this footing. Now this soil, let me try to make a complete sketch of this footing. Let me try to give us I think a three-dimensional drawing. Let's say if we try to draw, no, we can try to draw this way. We produce this way. We sketch this way. No, let's try to draw. Wow. No. Okay. Let me draw this one back. No. So sorry for the sketch, I try to make it snappy. Now this soil, this is our base. This is our base, and these soil pressures are acting everywhere within the base area. I just try to show it here from underneath our base area. The soil pressure is acting everywhere underneath this base area. Let us assume that this dimension, sorry, let's assume that this dimension is probably 1.5 or 1.2. Let's take it to be 1.2, and this side too is 1.2. We just want to take and this is 1, 2 as well. Then the thickness, which is here, let's just assume it is 300. These are assumed value. We just want to play around these figures. Now, and this is what we have chosen, and there is a force N, which is our load from our column through our slab and through our column. The force from the slab and beams are taken. So let us assume it to be N. And as this column is acting on this base, let me try to make it clean up this place so that it looks something good. As this column is acting on this base, the soil pressure within this base area, which we have chosen as 2 by 1 2 by 300 mm thick, the pressure will be acting under this. Let's say it is P. This pressure is P. Is acting underneath this base, the entire area of this base. Now, if this happens, like we said before, it is being carried out in lab or probably in site, and it was discovered that there is tendency that as this pressure is pushing underneath this as this pressure is pushing underneath the soil, underneath the base, the soil pressure is pushing underneath the base, that there is tendency. There are three things that can happen, which we are going to take one after the other. There is tendency that this footing can bend. So let me try to draw it here. There is tendency that this footing can bend in this manner. It can bend in this manner. This footing can bend in this manner. This footing can bend in this manner. Can bend in this manner. Sorry, we are using a sketch that is not easy to draw. Yes, so this footing can bend in this manner as this load is acting on this beam, on this footing, as this column load, which we are talking about from this place, is acting on this footing here. There is tendency that this footing can bend in this manner, and that means that for it not to bend this way, what is the solution? The solution is that we need to provide reinforcement. We need to provide reinforcement in order to keep this footing from not bending in this manner. That is the reason why you see reinforcement in your footings. So they are not just there for fancy, they are there to prevent this, what we call this bending moment. So you need to provide this footing in this manner in order to stop this moment from taking place. So that is the reason why we place reinforcement in footing. The reason is for you to arrest moment. And this reinforcement is meant to be at the very bottom of this footing. So let me make a sketch trying to show us where this reinforcement is, and to also show some pictures as well. So this is the footing, the reinforcement we are providing in order to stop this footing from bending this way. So that is why we provide reinforcement? We provide reinforcement to take care of this bending moment. Now look at some pictures to help you. You can see this footing. You see how the reinforcement runs from this way along the x-axis and along the y-axis. The essence of this is to prevent you from having a bending of this nature so that your reinforcement can be in the shape it is. We also have other images here. You can see with this live image, look at how your reinforcement is running both in X and Y direction. I'm going to explain the essence of this reinforcement that you also see here as well. So we provide this so that this thing will not bend and give us a shape that is not, because when this happens, your footing will crack. And once the footing cracks, there is tendency that the column within that area can settle, which can lead to either a collapse or send crack throughout that portion of where the column is supporting where the footing is supporting that column. So, and these things we don't want to happen. So that is why we provide. So you provide reinforcement in footing to take care of what? Bending moments. So the second thing that happens to this footing when it is under the action of this load is that there is possibility that this footing can shear. This footing can shear. Let me use a different color. There's possibility that this footing can shear into two. It can shear. There's possibility that it can shear into two. Let me make a sketch trying to show you. And that is the second reason why the reason why we need to check the thickness of our footing if it is adequate, or why sometimes you see that the top reinforcement also is being provided. I will show us the sketch now. Now if you have a footing this way, if you have a footing this way, now okay, we have done the sketch and we are looking at this same soil. It's acting everywhere. I just don't want to, because of time, I don't want to start sketching it both inside, but this is a replica of what we are saying. As the soil is acting everywhere underneath the base, I only try to draw only the ones outside because of time. Now, as this happens, there is tendency, this is our base, and this is it here. There is tendency that as because of the action of this load and the action and the reaction of the soil underneath the base area of this footing, which we have here as well, there is tendency that this base area can shear into two, which is what I have drawn here. Let me try to make it look. It can shear here, this way, can shear this way through the depth along this width. So there is tendency that as this pressure is acting on this footing, this footing can shear in this way. So this is what we call the one-way shear or direct shear. So these things happen to this footing under the action of the load. So what is the solution here? If as a designer you are designing and you find out that because you have to check what we call in order for you to be able to arrest this kind of situation, you have to check that your shear stress, V, let me call it ultimate shear stress, just put substitute should be less than your VC. In our calculation, you will get to understand it more. But I just want to explain why, how and why you can, how you can arrest this situation if you are designing and it happens that when you check for one-way shear or when you check for direct shear, it happens that it's failing, what you can do to arrest this situation. And as a designer, because the thickness of this your base is, if it's getting more than 550, if it's getting more than 550 when you are designing, or probably 600, it becomes kind of ridiculous for you to choose a base thickness that is higher than this 150 or probably 600, because you might be requiring so much reinforcement to cater for the load that is coming. So if you take your, as a designer, you have chosen a thickness of 150. Let me come back to this. If your ultimate shear stress is less than your concrete shear stress, it means that this thickness that you have chosen is sufficient, and probably you will not be needing any shear reinforcement. But if your VC, when you are designing and your VC is less than your let me say V ultimate, for example, it means that you'll be requiring shear reinforcement. That means you have to provide reinforcement at the top of this footing. Now, look at this one. When we talk about moment, we provided reinforcement at the bottom of this footing. That means you have to provide a reinforcement at the top of this footing this way. If that happens, you have to provide reinforcement here. You have to start providing reinforcement at the top of this footing here in order for it to take care of this shear. So let's say, for example, you don't want to, you have, maybe you have chosen a depth, because if you want to make if probably when you calculate your shear, your ultimate shear stress is greater than your concrete shear stress, then you have to increase the depth of this footing. But let us assume that you have increased the depth of this footing and is kind of higher than this 600, and you don't want to go more than 600, and you still want to use pad footing. You don't want to change the type of footing, maybe to raft or strip. You still want to maintain the pad footing. Then that means you now have to provide top reinforcement for that footing in order to cater. So that top reinforcement is now going to take care of this shear. So remember, as this thing is shearing total, if we provide reinforcement this way, sorry, let's reduce it. If we provide reinforcement this way, if we provide reinforcement this way, we provide reinforcement this way at the top. Are you seeing it? It will prevent this crack from taking place. So you provide it both horizontally, and vertically. You provide a reinforcement both horizontally and vertically, provide reinforcement both horizontally and vertically in order for it to take care of this shear that can happen here. And the code is saying that there's what we call critical section. At this shear can happen anywhere within the slab. There can be shear here, there can be shear here, but the code is saying that the shear is critical, because in design, what you look at is the critical part, like where you have the maximum bending moment. That's the moment that you take to design for reinforcement. So the code is saying that this shear is usually critical at a distance of d from the face of the column. From this face of the column to here, that is, if we have this footing here, let's look at this footing. Let me bring out this real life footing here. If we have this real life footing here, you understand? If this footing want to shear into two this way, if it wants to shear into two this way, the code is saying that this footing, when the pressure is acting under it, it is from a distance of 1.5 d, maybe probably around from where here. That is where you can see this footing shear into two. So that's what I have tried to represent here. It will shear into two at a distance of at a distance of d from the face of this column. That's where you are likely to see this crack or this shear from your footing. So if you have you want to still maintain your footing, but your thickness is now exceeding 600 or probably 550, and you find out that your ultimate shear stress is still greater than the shear stress of concrete, because this shear stress of concrete has a value that has been derived by code for you to check. If this one is the ultimate shear stress is less than your shear concrete shear stress, you wouldn't need to increase the section that you have chosen before, and you won't need this top reinforcement. So most times when you see a footing that is not that is not that is supported this way, that is not a combined footing, and you are seeing the double the footing carrying both top and bottom, you should know that this is a situation that has occurred, and the designer is trying not to go further by providing this. But ordinarily, if your thickness is okay, you don't need to provide any top reinforcement. If you increase your thickness, and as you're increasing the thickness of the footing, and you find out that it's okay, and within this 5 years, you don't need to provide any shear reinforcement, which is what we have done here. Sorry, you don't need to provide it. So you use the thickness. So this is also one of the things that happen when load comes on these things. We are going to be in our B series class, we are going to derive the calculations that dealt with these things, both for bending moment, this and for also. So we are going to the last one, which is the punching shear. Now, punching shear, we let us make a sketch and try to show what happens also when these forces are acting on the footing. Now for the punching shear, this is the diagram we have sketched. Now there is another thing that happens to footing when it comes under load like this, is that if this value n is so big, there is tendency that this column, this is the basis of our drawing. I've tried to sketch it in a way that we understand it. If this column, there is tendency that I'm just making a section view of this map. So if this column, there is tendency that it can puncture through this footing. And when it does that, it will puncture, look at it this way, it will cut it within this side like this and puncture through down. And once this type of thing happens, it leads to collapse. It leads to collapse of the building. These ones may probably lead to maybe service limit state. This one too can lead to that, but this would definitely lead to collapse once the column punches through the footing. So you need to check for punching shear to make sure that you choose, and punching shear has to do with thickness of the base. It is still the same checking your VU as against your VC. So if you check it in our analysis class, we are going to show these formulas and try to do some examples for you to understand and see. But I need to break this place down. This is where that can be difficult for you, because if you are designing or you are making a calculation and you already know what happens to what you want to do already, you know that okay, you want to design for moments to cater for reinforcements that will prevent this thing from bending. You know that you want to check, because it is three things that is being discovered that can happen to this footing, and you want to check for one-way shear. You check for the one-way shear. You know that you're supposed to check for one-way shear to know whether you provide shear reinforcement or probably also increase the thickness of your footing to make sure that situation like this doesn't happen. Then three, you need to also check that VC, that your own why we are using ultimate V is because by then we have loaded the structure. So, but this one is a formula that has been derived that you must check to make sure that this thing doesn't puncture through it. You must check it via your calculation to make sure that it doesn't puncture through it. So now, when we check VC should not, your ultimate U should be less than VC. But if the reverse is the case, if your VU, which is your ultimate shear stress, is greater than your VC, definitely this column will puncture through that slab thickness, that footing thickness that you have chosen. So how do you solve this problem to make sure that when you calculate it and you see that your shear stress which you have calculated, ultimate shear stress, is not greater than this, you have to increase the thickness of this footing. So why we check for punching shear is to also check that the thickness of the footing is adequate. If we check and the thickness that we are choosing, for example, we have chosen 300 here. If we do our calculation and find out that VU is still greater than VC, we have to increase this thing maybe by 350. You can increase it in multiples of 50. So you can increase to 350. You check again from your calculation. Then if it's failing, you still move it to 500, move it to 550, and still check. You must make sure that you're punching shear. Now let me try to show us a video of how possibly, a picture of how possibly this column can puncture through our slab. This is a free, look at it here. If the thickness is not sufficient, can you see when this load is acting here, when the column load is acting here, which is what I have drawn, which is what I have tried to sketch here, this column load here, you can see how this column puncture through this slab. Can you see it? Can you see how this column punctured through this slab? Because the thickness of this footing wasn't sufficient enough. So that's why this column punctured through this slab. You can see the area through which the thing punctured and passed and make a hole. So this one will give us a total collapse. So, and let me try to explain to us here. For this to happen, when it punctures, the code is telling us that the possibility is that this puncture can take place if we try. This is our column. Let's take the center here, look for another column, and this is our column here. Now the code is saying that there is possibility that this puncture, when this column punctures through this column, it will do that at a distance of 1.5d. That means from the face of the column, 1.5d, 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 1.5d. So that's what this thing will puncture. That's what I have done here. This thing will puncture through this place like this. at a distance of what? 1.5 D. When we want to do our calculation, you will get to see how to calculate all these things. But in this A series, we are just concerned about explaining what is happening around the footing, what you need to check, what you need to know, why you are providing your reinforcement, why you most times if you're designing and your footing is failing under shear, why you can take you can provide top reinforcement to cater for this kind of failure here that you have here. So now this can happen too. What do you do here? If you calculate that your ultimate VC is you increase the thickness, you can now increase it from this 300, you can take it to 350, 450, and all of that. Now there are things that most times you will see some step footings like this. Let me try to show us. You see something like this. You see what they are trying, this image is trying to show you here is that because they have checked and see that this particular thickness will fail under punching, instead of making this thickness, let's assume that this is a 450 all over the maybe under one way shear, this one passed, this thickness was sufficient, but under punching shear check, maybe the thickness wasn't enough. So what they did, instead of casting this whole thickness, they now took 1.5D from the face of this column and cast only this part because they want to be economical in the design. So that's why sometimes when you see footing being stepped like this, the essence is they are trying to create and take care of punching shear. So when you see things like this, just know that they are trying to take care of punching shear. That's why they are making it, because if they decide to cast this thickness of this footing around this whole base, it will be very expensive. So they economically designed this footing to be like this. Let me also show us this video. You can see it here, what they did here. They don't want to cast this full base up to this point. So they increase from the face of this 1.5D, because this is from this distance of 1.5D is possibly where this punching shear can take place. So that's why they make a reinforcement. So when they will cast this place as another level, maybe let's say 300, then they will cast this place maybe at 550 or at 600, just to take care of the punching shear. So today, I want us to know that that's the reason we are taking this. And this punching shear, you see, from this image, the you can see how much of this concrete that this thing, when it punches down, it went down with some concrete. That distance is 1.5D. That it has been discovered that there is possibility to push that whole area down, to push this whole area here from the face of this column. When it's punching down, it will punch through it. Also, that's what we want to explain here in our next class. We are going to treat another structural element. We have talked about footing here, and I hope you get what we are saying. I'll try to make an outline of what we'll be checking. I'll write it down for us to understand. Okay, let me make a recap of what we have learned today. We have learned that our footing can be possibly bend, which is the bending moment. We have also talked about our footing being able to shear, which is the one-way shear here, or probably called the direct shear. We also look at our footing being able to puncture, which is this, through our column puncture through the footing, which is the punching shear. These are the three things, and probably the three-way or three circumstances that can happen to our footing. We have also seen the reason why we provide reinforcement, and sometimes why you see some footings also have both top and bottom reinforcement. I've tried to make a sketch of the moment here showing you we have also looked at this point. So we are going to call it a day, and thank you for listening. Don't forget, we'll be treating many of these kind of situations and for you to know. So if you are if you are a site personnel and you are given structural detailing, you ensure that you carry the structural detailing, you carry what is in the structural detailing out properly, because you will already know that situations like this can occur, and for the designer to have provided this, yeah, he's trying to prevent this type of situations. Don't be um don't don't play with it. Don't try to play with these things. They are very, very important, as we may see on site in so many places that they try to put footing, they try to build without putting even footing in their foundation. So you don't have to do such thing, because now you already know what is happening around your footing. And thank you very much for that.